Okay, so on the way in, there are two packets. There is the 2018 multiple choice exam. That's no different than the other ones I've really given you. I mean, it's different, but like in terms of content, it's a multiple choice test like I've given you 3 others. The other packet is a review packet of every unit 1 through 7. Okay? It starts with a breakdown of topics and then review questions from unit 1. A breakdown of topics in unit 2, review questions from unit 2. A breakdown of topics in unit 3, review questions from unit 3, so on and so on and so on and so on. This is obviously an insane amount of chemistry, and I've provided for you 4 multiple choice exams as well. And I also emailed you the link of free response, which was 5 free response questions, or 5 free response tests. Needless to say, I've kind of been bombarding you with just an insane amount of stuff, right? The hope is that you're certainly using the resources. I can't imagine you're getting through everything. I mean, sure, yeah, absolutely. Please, again, the more you do, the better off you're going to be next Friday. There's no doubt about it. And my hope is that I've given you so much that you can't possibly get through it all. I mean, that's not really like, I don't know. Again, I want you to do as much as you possibly can, but I am probably giving you too much. But that's sort of by design, because I'd rather have it be on that end of the spectrum than not providing you with enough materials. The answer keys to all of these review packets are already posted. If you go to the resources tab under our It's Learning page, there's a folder titled AP Test Review, I think is what it's called. And it has, you know, these documents as well as the answer keys to all 7 units. The way I would use this, well, first off, we'll use this next week in class, meaning I'm going to hit some of the high points from this, okay? We will use this as like revisiting unit, especially semester 1 stuff. We're going to talk about unit 3 quite a bit next week, because I think unit 3 is the biggest unit on the exam, and it's been quite a bit of time. Intermolecular forces. Yeah. Okay, so we'll use this next week in class. Folks at home, I'll obviously have a stack of these downstairs. If you can sneak in over the next couple days, I'd recommend it before next week, Monday. And yeah, that's where we're at. Questions at all? Tomorrow, let's talk about tomorrow. Tomorrow, I'm blocking off my entire morning to help. Here's what that means. If it's before 11, and you're in the building, come up to the chem room. I'll help you. Okay? You can either make plans to do that, or if you're just randomly here for something else and you got a split second, or you're in between other group club meetings or whatever, please come on up. I'm going to leave my afternoon off limits. I got stuff to do. Obviously, I can't just sit around and help you guys all day, but not that I wouldn't mind doing that. But so tomorrow morning, I'll run the official session at 10, like I've been doing for the last couple of weeks. And I'll record it and I'll post it and all that good stuff like I've been doing. But prior to 10 a.m., I get here at like, I don't know, 7:05, 7:10-ish. Not that I would recommend getting here that early, but if you're around and you're going to be potentially looking at stuff anyway, you're more than welcome to come to the chem room anytime tomorrow morning prior to 11 o'clock. Just, it's an invitation. Take it or don't. Doesn't matter. Just let you know. Cool? Yeah, yep, at 10 o'clock we'll do free response. I'm only going to do free response for those sessions. I think that's slightly more daunting for most people. Maybe not for everyone, but I think the majority of people view the free response as the scarier of the 2 sections. But anything at all? Okay, cool. Let's go through 9, 10. So today, we are going to talk about electrolysis and Faraday's law. It's really taking what we've done so far and flipping it on its head, meaning we're going to take what was previously a galvanic cell, and we're going to force it to run backwards, okay? We're going to force our galvanic cell to run in the opposite direction that it thermodynamically would like to run. So I have 2 galvanic cells side by side, exact same stuff. And the very first thing I'd like to do is figure out what my reaction is. Okay, I want to set up an oxidation and a reduction in the direction that gives me a thermodynamically favorable galvanic cell. So thermodynamically favorable, what am I looking for? How do I know if a galvanic cell is thermodynamically favorable? Positive cell potential, positive E, positive voltage, however you'd like to say that, right? I need a positive overall cell potential. So let's take our two processes. If you could, old periodic table, if anyone's got one around, find the reduction of copper, because we have copper on the right-hand side, we've got zinc on the left-hand side. Find the reduction of copper, find the reduction of zinc, and let's figure out which one we got to flip and turn into oxidation. Again, what's the goal? The goal is a positive cell potential. So you find the copper one. What's the reduction potential of copper? Positive 0.34 volts. What is the reduction potential of zinc? Negative 0.76 volts. Which one do you want to flip to oxidation? That sounds like a great idea. If we flip the zinc one, it's going to turn it from negative 0.76 to positive 0.76. And then when I add that to the reduction of copper, I would have a positive overall cell potential, which is exactly what we're looking for. So let's write that out. The oxidation is going to be zinc metal being oxidized into zinc 2 plus. And what was the oxidation potential again? Positive 0.76 volts. We'll keep the copper in the direction that it was given to us in the table, and we're going to have the reduction of copper 2 ions. And what was the reduction potential of that half reaction? 0.34? Yeah. And the overall process. Now, in reality, we would have to like balance each half, but this is about as easy as life could ever get if you're taking a peek at it, right? We've got zinc losing 2 electrons, copper 2 ions gaining 2 electrons, so that it's already balanced and everything's just 1 and 1 and 1 and 1. So we don't have to do the whole craziness. We can just kind of glance at it and realize that we're kind of good to go. So I have an overall reaction of zinc plus copper 2 yielding copper plus zinc 2. And the overall cell potential equals positive 1.10 volts. Make sense? That's old news. So let's change it a smidge. On the left-hand side, I have a normal working galvanic cell going in the direction of thermodynamic favorability. On the right-hand side, I'm going to do something else. I'm going to hook up this cell to an external power source. And I'm going to force this to run opposite of what it wants to. I'm going to force it to run backwards. So here's my question to you. How many volts of electricity do you think I need to supply in order to make this thing run backwards? No.
More than 1.1.
Yeah, great guess. More than 1.1. Because if I'm not supplying 1.1 or greater than 1.1, I don't have enough energy to force it to run opposite of what it naturally would go, right? In the spontaneous or thermodynamically favorable direction, this is going to run with 1.1 volts. So if I want it to run the opposite way, I better supply more than 1.1 volts in order to accomplish that. That seems pretty intuitive. Let's label these two diagrams, okay? The left one is the normal galvanic cell. And by galvanic cell, I mean voltaic cell. And by voltaic cell, I mean electrochemical cell. Right? Okay. So what's happening on this side? What process? Huh? Oxidation. What's happening on this side? Thanks, Jack. So if oxidation is occurring over here and reduction is occurring over here, well, how are the electrons flowing? Left to right. Because this is the half that is losing the electrons, this is the half that's gaining the electrons. So I would expect that flow to be from my left side of the cell to the right side of the cell through that wire. What would I label as the anode? The zinc electrode is going to be called my anode. Because oxidation occurs at the anode. The copper electrode is going to be called a cathode, because reduction occurs at the cathode. Sound good? That's all old news. We've done that previously. But now let's take a peek at the other one. In the other picture, the difference is I've switched out my voltmeter for a power source. Okay, my voltmeter, all that does is tells me what the voltage is. So this little box right here, if we hooked it all up, it would say 1.1 volts. Cool. But let's switch that out and let's put something else in there. Let's supply energy and force this to run backwards. Okay. When we force this to run backwards, what process would I have occurring in each of my two halves here? Reduction would be on the left. We're forcing now the zinc to be reduced, and we would be oxidizing the copper. And as a result, which way would my electrons flow? Right to left. And if oxidation is occurring on the right-hand beaker, where's my anode? Anode's the copper now, right? And the cathode is, I'll go like this. Aha. The zinc. I'm have to write it again. How exciting. So those same terms still apply. Even though I'm forcing this to run opposite of what it would thermodynamically like to do, I would still call the electrode where oxidation occurs the anode. And I would still call the electrode where reduction occurs the cathode. So those terms are still going to be where they're supposed to be. Okay. So this is called an electrolytic cell or electrolysis, depending upon the context. Let me scroll down. So cell B has an external power source attached to it. Again, how much voltage do I need to apply to make this to work? Well, it better be greater than 1.1 volts. Okay? Because if it's not greater than 1.1 volts, well, then I haven't supplied enough energy to get it to go opposite. Cell A is what we know. Cell B is called an electrolytic cell. Okay? It's when you force your galvanic cell to run opposite. Again, I've said this example multiple times already. Cell B is like charging your battery. Okay? Cell B is when you plug in your cell phone into its charger. You're forcing it to go opposite of what it would like to do. And you can achieve that if what you're supplying as an energy source or a power source is greater than the voltage of the spontaneous or thermodynamically favorable direction. Cool? Okay, so what does this lead us to? How can we use this? What purpose would running a galvanic cell backwards serve? Okay. So in an electrolytic cell, if we know how much current is being supplied. Now, we're getting very physicsy here. When we talk about potential and voltages, and we talk about current, in other words, again, electricity flowing, okay? We're very much getting close to physics, and I don't like it. I don't know a ton about electronics or electrical systems. I don't know a lot. Talk to Ms. Gates if you're interested, or take more physics in college if you're interested, okay? But for our purposes, we're going to talk about current just a little bit, and current is measured in amps, okay? What is an amp? An amp is how much charge, aka coulombs, I am transferring per second. The quantity of charge transferring per second that I have my electric system working. Okay? So coulombs are the unit of charge. And we can quantify the total charge transferred if we know how many electrons are transferred, because we know the charge of a mole of electrons. That's called Faraday's constant. Faraday's constant tells us that when we transfer 1 mole of electrons, we have transferred 96,485 coulombs of charge. So we're going to do this factor label style. Okay? We can answer questions factor label style using the current being supplied to an electrolytic cell. Sounds kind of fancy, but we're basically doing old school factor label stuff that we taught you last year. But this time we're using the context of like redox reactions and electricity. But we can figure out ratios, we can set this up, we can cancel out labels. That's kind of all old news, and we're pretty good at that, I think. So this equation is in your packet. Capital I stands for current. Q, unfortunately, is for charge. I really wish they would just have capital C here. That's not the way it goes. And then little t is time. So how much charge is transferred per second is what an amp is, and what the current is measured in. Let's give you a hypothetical situation. Up above, we had our zinc and our copper cell. And the question here is, well, how much zinc would I get on the cathode if I were supplying 10 amps of current for 30 minutes? Let me go back just a second. And let's think about the anode and the cathode for just a little bit. The anode is where oxidation occurs. Oxidation is when I turn my metal into ions. What happens to the mass of the anode over the course of time? If I'm turning metal into ions, what happens to the mass of my anode? It decreases. It's going to go down. I'm taking those metal atoms in my electrode and converting them into aqueous ions. What happens to the mass of my cathode on the other side? I'm reducing ions into metal. In other words, these copper ions over here are turning into copper metal. So the mass of my cathode is going to increase. So as the battery runs, the anode is going to decrease in mass as it becomes oxidized. The cathode is going to increase in mass as the ions become reduced. So what's cool about an electrolytic cell is if I know how much current is being supplied, and I know how long that current is being applied, I can figure out exactly how much mass of metal I'm depositing on the cathode. That's what this problem's trying to do, basically. It's trying to take an electrolytic cell, pump it with electricity, and then based off of how long it's on and how fast the flow is of charge, what mass of metal can we possibly produce? Sorry, sounds scary. Let's try this. It's not bad. I want to start my factor label problem with time. But I don't like minutes because my amps are given to me in coulombs per second. So instead of using minutes, let's first convert that. So it's a unit that matches something else, right? We need matching units or labels so we can obviously convert between various things. So I'm going to turn my minutes into seconds. And then I'm going to turn my seconds into coulombs, because I have an amperage or amps being applied. Okay, so I have, for every 1 second, I'm going to get some coulombs being transferred. Sorry, I'm going to shut this door as well. I don't think we're having too much fun. It's not all my class. That nonsense. So I'm taking the amount of time figuring out how much total charge I'm transferring. And then based off of that total charge, I can figure out how many moles of electrons that equals. Because I have a conversion. I have that Faraday's constant, which says the total number of coulombs per mole of electron. And then I'm going to convert from moles of electrons to moles of what I'm actually interested in. In this problem, we're trying to solve for the mass of zinc. So there's a ratio. I know that for a certain number of moles of electrons I transfer, I'm able to make a certain number of moles of zinc metal. And then I can go from moles of zinc to grams of zinc using its molar mass. And this is the overall setup. It's kind of, extensive.
Reminds me of just chemistry last year.
Yeah. Kind of. It's weird. It's different. What's that?
Sort of like stoichiometry.
Yeah, more or less. Same kind of setup, right? Just different values and kind of a weird context. But if I run 10 amps of current for 30 minutes, how much zinc do I get deposited on the cathode? Because remember, at the cathode, we have reduction occurring. And when reduction occurs, aqueous ions are turning into solid metal. So we can determine how much solid metal would be produced based off of these values. So I'm going to plug everything in. How many seconds are in a minute? 12. That's wrong. How many coulombs are we transferring per second? 10 amps. And an amp is a coulomb per second. So 10 coulombs per second. It's 10 amps. That's an amp. An amp is a coulomb per second. So we have 10 amps. That's 10 coulombs per second. How many coulombs equal a mole of electrons? Faraday's constant. 9, 6, 4, 8, 5. How many moles of electrons do I transfer per mole of zinc? It's whatever the charge is, yeah. Because in reality, right, I'm taking zinc ions and turning them into zinc metal. Well, how many moles of electrons do I need to turn zinc ions into zinc metal? Oops. Yeah, I need 2. So this is a ratio of 2 moles of electrons for every 1 mole of zinc. And then I have the molar mass of zinc. What's the molar mass of zinc off your periodic table? 65 something? We'll go with 3.8. I trust APs a little more. And what do you get? I heard you take a guess again. You did well, didn't you? Yep. You're good. How many grams of zinc do we get produced? So again, this is kind of weird, kind of funky, but we have an electrolytic cell. We have a redox process occurring where if we monitor the flow of electricity, how many coulombs of charge we're transferring per every second, and if we know how long that current is being applied, we can actually determine how much solid metal is being plated or produced. Let me give you a little more context, because this is used in like the jewelry industry, but maybe an easier example is like old cars. Cars from the 50s had those big shiny chrome bumpers. Okay, the way they actually put the chrome on the bumper was they would take that giant piece of steel. Usually everything was super heavy back in the day, right? They'd take a giant piece they'd make the bumper out of like some ugly metal, and then they would take it and they would dip it in a solution filled with chromium ions. Then they would electrocute it like crazy. And as they sent electric current through there, the chromium ions in the solution were reduced into chromium metal. And they would plate on the surface of the bumper and make it all shiny and pretty. Okay, so this was a real process. So you can determine how much of a metal you're going to deposit if you can monitor the current and the time that you're applying that current. And it turns into a giant factor label problem. Okay, let's try a couple more.
Wait, is that it for webbing?
Not really. I mean, well, sort of, yeah. Let's pretend we are running electricity through molten iron 2 chloride. Now, this is a different context. In the previous example, we took a galvanic cell that was unfavorable and we forced it to happen. In this problem, what we're doing is taking molten iron chloride, which is an ionic compound. Now, when I say molten, what does that mean? Literally melted. Now, why does it get a special word? Well, because it's really, 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 really hot. When you think of molten, I'm assuming you probably think of like lava, volcano stuff, right? Yeah, kind of. So ionic compounds, melted, also get the term molten. It's liquid and it's extremely ridiculously hot. Okay, so that's the context. We have liquid ionic compound. Now, when ionic compounds melt, they actually ionize. So in other words, I have ions of both iron and chlorine in my molten pool of iron chloride. So the setup of this is quite literally the exact same in terms of how we do the math and how we do all the factor label stuff. What's different is the context that they're providing the problem in. But don't overthink it. What I'd like you to do is mimic what we did just previously from the problem right before this and set it up. Set it up factor label style. Try to figure out how many grams of iron we get produced. Go for it. Anyone thinking they're going to take me up on tomorrow morning? Morning? Yeah, don't be, yeah, I mean, again, I know there's a couple other people from the other class that were thinking about it too, so. No one shows up, don't worry about it. You teach things. But again, my goal over the next 8 days is to be hopefully very, very available for anyone and everyone who wants to study how things look at. Make me earn my pay. No, seriously, I mean, I mean that, like, very much so. Like, please use me as a resource as much as you can.
No way.
Did you guess again?
I mean, it took me 2 steps, but yeah.
We ready?
I have it.
A little more time?
No, you can just go. I know, like, where it's.
I don't want to inhibit your learning.
I did that to myself.
I mean, it is almost May.
Mhm.
'Tis the season of learning inhibition. Especially if you have a 12 behind your name in Infinite Campus. True story? It's all right, hang in there, seniors. You guys have like 3 weeks left.
Yeah.
That's
I
ridiculous.
just, once I get past the calculus.
Yeah.
And I think
Oh, I thought you were like done. Okay. Well, so you really can't too much check out in the next couple of weeks. That sucks. 20 minutes. Minutes aren't great for amps. Amps are per second, so let's convert to seconds. We're going to go from seconds to coulombs. Coulombs to moles of electron. That's an M. There we go. And moles of electron to moles of iron in this case, right? And then moles of iron to more grams of iron. Sorry. So 60 seconds in a minute. How much amperage am I applying? 15. How many coulombs are in a mole of electrons? 96485. That is Faraday's constant. It is in your formula packet. How many moles of electrons am I transferring per iron? That might be an issue, right? We got to think. Now, my compound is FeCl2. We know chloride has a 1- charge. So what's the charge of my iron? 2+. So what I'm really doing is I'm taking iron 2+ and I am reducing it to iron metal. So how many moles of electrons do I need for every 1 mole of iron? 2. And then the molar mass of iron is 55.85, right? And what do we get? How many grams of iron would I have plated or deposited in this process? How many grams?
It's like 1.
That's not. I think 5.21 sounds familiar. Did she just bait you into that?
Yeah, it's
Nice.
5.21.
Okay, hypothetical questions. If I had more amps, would I get more iron or less iron?
More.
More. Makes perfect sense, right? If you look at the fact label math, what would more amps change? It'd make that number bigger. And as a result, my final answer would be bigger. If I had this running longer or more time, would I get more iron or less iron? More. This one's even more intuitive, I think. Because it's like, oh, if I run it for 20 minutes, I get this much. Well, if I ran it for 30, I'd probably get more. That makes sense. How about the last one? Instead of this being iron 2 chloride, let's say hypothetically I started with iron 3 chloride.
You get less.
I'd get less. What changes? The ratio here, right? If this was iron 3 chloride, I would have iron 3+ plus 3 electrons going to make real iron, solid iron. So in that instance, this ratio would turn into 1/3. And if the denominator increased, I'm actually decreasing the quantity that I could possibly produce, right? So this would be less. Okay, so there's different ways you can mess with it, right? Like anything in this class. You can tweak a number here, change a number there, and conceptually, we should hopefully be able to kind of figure out what the heck that would do. Hopefully. Couple more problems. A little different, but a couple more. Let's think about these. The reduction of copper 2 to copper metal is positive 0.34 volts. The reduction of iron 3 to iron metal is negative 0.036 volts. Faraday is what it is. Volts are joules per coulomb. What are the half reactions for copper and iron if we want to make a galvanic cell that actually works? Okay, if I want to make a galvanic cell that actually is thermodynamically favorable, what 2 half reactions would I need? My options are using copper 2 and using iron 3. What one do I want to flip? The iron one. If I leave the copper one where it is, that's good. I have positive 0.34 volts. If I flip the iron one, I'm going to get positive 0.036 volts, not very much. But again, the end goal is to have a reduction and an oxidation that leads to a positive cell potential, a positive voltage. So let's flip the iron one. I'm going to have copper being reduced And the potential of that process or that half reaction is, sorry, 0.34 volts. And if I have the oxidation of iron, that's going to look like this. And what is the potential of that process? Positive 0.036 volts. And then the overall cell potential of this battery or galvanic cell would be positive 0.0370. Can I do math? 376? Let's try that. Sorry. Well, not really. I just, my brain's deteriorating in my old age.
Still got a lot.
Some days I'm not sure.
Yeah, same here.
Sorry, I just went Kyle Shanahan on you guys. And if any of you get that reference, good job. I can't imagine. Does anyone get that reference? Anyone? Kyle Shanahan? Excellent. You guys aren't following the draft. See, Jack, I would crush you tonight.
What? I can just guess that.
If you were following the draft, you would know exactly what that comment was, but never mind. I can't imagine most humans know.
Is he important?
He is the head coach of the San Francisco 49ers.
Oh, so no.
He was asked a question in his press conference, and his response was, "Well, we could all be dead on Sunday," and it had like nothing to do with what question was asked. It was very like,
awesome. He sounds like he's like really disappointed. That
Sounds like he's very
potential prospect.
no, it was something like it was quite the press conference. I don't know if anyone cares, but it was very weird and out of context. So like,
sounds like a
so the entire NFL world's just basically making fun of him right now.
Someone needs to like check up on him.
Maybe. Well, the problem is he's going to make a pick tonight that none of his fan base wants. So I think he's preemptively like,
Are they picking Sean Watson?
that would be a, no, they're going to pick Mac Jones, and none of their fans want that
Why?
because there's better quarterbacks.
Right, but
Yeah, like
can we
Deshaun
get
Watson.
those?
No, huh?
Can we get those better quarterbacks?
Yeah, because that's not what Kyle Shanahan wants.
Is that why would
So
we
he's
want-
preemptively preparing his fan base for sadness. And then he got put on the spot, and he got angry, so then he said that we all might die on Sunday or something. It was weird. Anyway,
Would you not want to pick the better quarterback? It doesn't make sense. That's like saying, oh,
That's-
I'm not going to take the best, like.
I mean, it's kind of a judgmental thing, right? Like analysis of player skill sets and whatever. But still, yeah, I don't know. Anyway, what do we get? How can I know if this is in the right direction? What is an indication that this battery is set up in the right direction?
The cell-thing is positive.
Positive voltage or a positive cell potential, right? If E cell equals positive, that means it's thermodynamically favorable. What's another indicator that would give me evidence of a thermodynamically favorable process? Oh, sure. If we took like lab analysis, sure, absolutely. Here. Anode, mass goes down. Cathode, mass goes up. How else would I know that this is thermodynamically favorable or set up the right way? Well, sure, yep. To say positive voltage.
Could you like calculate Gibbs energy?
Sure. If we calculated Gibbs, what should Gibbs be?
Negative.
What else? What should the K be? If K is greater than 1, that means the products are favored. Yeah, any of these are indications that we've done the cell or set up the cell in the appropriate direction. Calculate G if you could. We've got choices, don't we? How do we calculate G?
Let's do the one.
There's like 4 formulas.
I think that's the right choice.
Yeah, I know it.
Yeah, there's 4 equations in your packet that use Gibbs free energy. No, we're not doing trig.
I got a very important question. Would you consider yourself equally paid or qualified with this period in high school chemistry, struggling with the recent diagnosis, stage 2?
Wait.
In terms of like working with a former student and producing and distributing systems that stage piece of video while navigating the thing. If you consider yourself
This is the description of Google. Breaking Bad.
that's a part of Breaking Bad.
Yeah, yeah. He's living.
aware.
Yeah. It's Breaking Bad. Everybody knows about Breaking Bad.
That's what you would tell us. I'm secret.
Sure. You just open the.
You saw the scenes of Walter White teaching. They're not very good.
Basically,
What?
Seems like an awful teacher.
If you have.
They did all seem
That's because
miserable.
it's this period in high school.
Yeah, maybe I'm not this spirited yet.
Yeah, it's weird.
Who would be like Jesse?
It would be me. He doesn't have the technical know-how.
Neither did Jesse.
Wait, well, no.
Wait, did you just compare to be someone in this year would you?
You didn't answer my question.
None of this is applicable.
So.
Oh, no. He should be a method.
He used
Neither
the
is the
deepest
draft.
character in the show. Like,
It was such a good.
I'll
show,
think
too.
about it.
Okay.
Maybe I'll take application.
then you got the movie on there. I'll be Jesse. He's a little lost.
Yeah, that is not the plot of my life.
That's still what you
Sure.
would tell us.
TV, if you could like relate to a TV show character, what TV show character do you think you relate most to?
How long is it?
Just anything you've seen.
I want to say it's Ted Lasso, but there's no way I'm as happy as Ted Lasso. I aspire to be Ted Lasso, if you are familiar with the show Ted Lasso, which I've told you to go watch, and I still stand by that statement. You should go watch that
I'm
show.
not super familiar.
I wanna
but
say
did
it's
look
like-
it
It's
up.
phenomenal.
I looked it up.
I would want to say it's like one of those comedy family shows, like this single family guy, and it's just like this regular.
No,
And then there's just like wild adventures.
I feel like I'd be a pretty good sitcom dad.
You'd be a great sitcom. You definitely got plenty of dad jokes.
Oh,
You just have
100%.
dad energy.
Thank you. I think.
It's not a bad thing.
I don't think it's a, yeah, I took it as a compliment. How many moles of electrons are we transferring? Yeah. How do I know that?
Count it.
Yeah.
Well, again, we have the oxidation and reduction, right? We figured that out earlier. But now we got to figure out how many moles of electrons transfer between those two halves. Well, however many I gain, better match however many I lose, right? So right now, they don't match. So I'd have to multiply this by 3 and this by 2, and then the grand total of electrons transferred would be 6. I think that's the hardest part, right? We got to make sure we get the right number of electrons when we use that equation. But I don't know. Hopefully we're understanding where that's coming from now. I have 6 moles of electrons. Faraday's constant is 9, 6, 4, 8, 5. My cell potential is positive 0.376 volts. What do I get for a value of Gibbs? Say that again.
Negative 2.18 times 10 to the.
What is my label?
There's.
Nice try.
That would be joules, wouldn't it, if it's that?
We wrote it down a couple. It'd be kilojoules over mole.
Tis joules. How do I know it's joules?
Because that's how fast we're able to work.
Because they didn't change it to.
Well, again, let's go back to our units, right? What is the unit of this?
Mole.
Moles of electrons.
Oh, and then.
This is coulombs per mole of electron. So if I just multiply these two, I would get coulomb. And what is this? This is volts. Volts is joules per coulomb. So it's joules. Yeah. And again, here's the other dead giveaway, right? We're solving for Gibbs. Gibbs needs to be in joules or kilojoules, one of the two. And no matter what context, right? If I use any of my Gibbs equations, the end label or unit of Gibbs must be in terms of joules or kilojoules. Just depends upon what we use, I guess. But let's do number 4. Number 4 has nothing to do with the previous 3. I don't know why I clustered these together because the last one is quite literally independent. But try one more time. Try one more of these electrolysis questions. How many grams of aluminum would we produce in 44.4 minutes if I run a current of 8.88 amps through a molten aluminum fluoride solution? Okay. Hot batch of, I don't know, my phrasing there is weird, but Yes. Because the oxidation portion is
Wait, you supposed to be in there?
Yeah, you put him on the-
Yeah, that's what he gets. Right. I thought he called me Jesse.
Well, I don't know.
I thought he started it. He does. What?
He said he didn't want you to be Jesse.
No, I said
he
I
wanted
would
to be
be
Jesse. If I told you this wasn't the first time this conversation has ever happened in my teaching career.
Yeah, then back.
I've got the J.
He didn't ask me first, no.
Really? He was the one that came up. with
Previous
it.
years, I've had this conversation. This is like the fourth time I've had this conversation in my teaching career.
Probably just like.
Evidently, lots of kids are lining up to be my criminal accomplice.
Because Jesse was a good guy. Everybody liked Jesse.
He was a great character.
Yeah, it's like Jesse was like a good guy pretending to be bad, and Walter was a bad guy pretending to be good.
Sort of, kind of. I don't know. Like their arcs went in completely opposite directions. Like Walter White was genuinely a good dude early on,
Well, like Jesse was.
and then he turned into a horrible, horrible person.
He was always a horrible person. That's the whole point. Like, he
I mean,
was
maybe,
always a
kind
bad
of, I guess,
person.
if we're getting
He was a bad
philosophical.
teacher. He hated his accomplishments.
If we're getting philosophical, yeah. But then Jesse was like
Like he loved
an idiot,
Like that was his
kind of
No, but
loser.
he's like,
His story arc was really good.
His story arc was he was
Really
the
just-
captain that he has, that's insane.
Did you know that he was supposed to die after season 1?
What?
The character was supposed to die after one season of Breaking Bad, but then they rewrote the entire show to keep him on because Aaron Paul, the actor, was like he did such a good job. They completely like changed the show.
Wow. I
Yeah.
can't imagine.
I know that's why they kept him, obviously, because it was just
How many seasons?
5.
I don't know.
But really, it's kind of like 6-ish because the fifth season they split in half.
Yeah, but then there's a movie too.
I've been meaning to watch it, but then I just never.
Oh, it's good.
You can just burn through it in like 1 weekend if you really.
Oh.
Maybe 1 weekend's a stretch. But 1 week.
Even a week's a stretch. It's over 60 episodes. 45 minutes an episode.
They like
How
just
many,
get really
how
bad.
long is each episode?
It's like 45 minutes.
It's
That's like.
but like it just
Yeah, I mean, you're approaching 50 hours of television. That's a lot of.
How many modes?
Right.
Oh, really? Oh, shoot.
How many amps? 8.88. I have 9, 6, 4, 8, 5 coulombs per mole. How many moles of electrons do I need to transfer per mole of aluminum? 3. It's all based off the charge, right? So aluminum fluoride would be AlF3. My aluminum ions would be 3 positive in charge, so I would need 3 electrons to transfer. So this would be a 1-to-3 ratio. And I would go from moles of aluminum to grams of aluminum. And the molar mass of this is 26.98. How many grams of aluminum would I get? There you go.
That's the last one.
That's the last one.
Look at that, we're done with the phone guy.
Oh my God, wait, wow.
We sort of kind of are, yeah. I mean,
We're not doing number 2, almost number 2.
you can, I don't know. Sure.
Well, don't assign it, just give it,
give me some time.
pat on the back.
Kitty points, kitty points. How about some kitty points? I could use some.
We're gonna do like a little mini unit of organic chemistry after the exam.
Yeah, we're gonna do a smidge of nuclear, a smidge of organic.
Is that mainly
Did you
for
say nuclear?
Yeah. Say that again, Derek. Or Dylan?